Morning, everybody, to the fifth lecture of this GIAN short course. Today we will speak about piezoelectric material behavior. And I was told that the slides from yesterday were uploaded to the GIAN folder. Did you already reach it? Did everything work out? Yeah. Okay, perfect. So you can have a look afterwards, and I think we will do the same after this day. So in the evening you get also the slides from today. Quick look on the schedule. So we are today at day 2, first lecture, piezoelectric material behavior. After the tea break, we will have the first lab, blocking force and work diagram. And then we have a second lecture after lunch about electroactive polymers and also shape memory polymers. And then we close the day with the second lab, butterfly hysteresis. So today only 2 lectures and 2 labs. Okay, we start with a short introduction again and also a short recap from yesterday, and then we will go over to the piezoelectric material behavior and how to describe it with easy or simplified models. So the learning objectives for today are that you know the most important key parameters of piezoceramic transducer materials, and that you know models to describe the piezoelectric effect for small signal behavior. And also that you know what small signal behavior is compared to large signal behavior. So recap from yesterday, we introduced the large signal behavior of the piezoferroelectric functional materials. We saw also the butterfly curve on in the experiment in the evening, but we can quickly again go through it as a recap because it's really an important plot and could also be part of the exam. So if we start with an unpolarized piezoceramic material, we are here in point A. The polarization directions are statistically distributed, so we have no macroscopic effect. Then we apply an electric field up to the maximum electrical field we can apply without breaking the piezoceramic. Then we are here in point B. We have a really strong polarization in one direction, and if we then remove the field again, we come back to point C. Here we have 0 electrical field, but we still have the polarization of the piezoceramic, not that strongly orientated like with the field applied, but still a usable polarization. And also due to that, we have here a remnant strain between this point and this point, comparing the unpolarized piezoceramic with the polarized one. And you could also shift up this butterfly hysteresis and define that this point A is 0 strain, so it depends on the definition. So we are coming back from a high field to a 0 field, and if we then apply a field in the other direction, then we come down to point D, which is marked by the coercive field strength, or the negative one, and this is the point where we have polarization in the opposite directions, and we again have no usable or macroscopic usable polarization. And then we go up again to the point D when we increase the field again. Here we have a strong polarization again, but in the other direction compared to point B. And if we then decrease the field, we are coming to point F, which is the corresponding point to point C, but again with the other direction. And this is the large signal behavior, so between minus Emax and plus Emax. We don't use the whole range when we technically use this piezoceramic materials. We are using it typically between 1/3 of minus EC, so coercive field strength, and up to half or 50% of Emax. So these yellow arrows and yellow lines indicate the usable range and also the hysteresis behavior with the area enclosed by these curves. Yes? How we can calculate it? I'm not sure if we can really calculate it, but it's for the material always specified, so you know it from the data sheet of the material. And you also see it if you do the experiment. If you increase the field above Emax, you would get here a straight line. So the displacement or the strain would not increase anymore. So if you increase the field and the strain or the displacement does not increase anymore, then you have reached Emax. If you yeah. This value here, you mean? It's just defined so it's a definition by the user, so to say, to have a safe distance from this Emax point, because if you are going to Emax or above, you could break the piezoceramic, and to don't have any risk in operation, you want to stay away from Emax, and therefore you define this limit of Emax divided by 2. Okay. Okay. So we are now going to have a look in the linear piezoelectric parameters, which is specified as small signal operations. So we linearize the behavior and do not take into account this nonlinear behavior and this hysteresis effect for simplified modeling. We also had a look yesterday at the measured values. So here is the electric field over displacement. We start with 0 field and 0 displacement, and then have the initial or repolarization up to point P2. This would be Emax, 2.8 kilovolts per millimeter. And if we then remove the field, we have a remanent displacement or remanent strain of, in this case, 40 millimeter displacement. And here again, a measured hysteresis curve, electrical field up to 2 kilovolts per millimeter, and we can see here the path going up. If we increase the field, we are at 0.2, about 14 millimeter displacement, and then if we remove the field, we come back to 0.1. We have some characteristic values or unities here in the butterfly curve. We have the coercive field strength, which is this point and this point, where the polarization is lost, and it's the turning point between the directions of the polarization. And we have the maximum, and it's not signed in here, but here the opposite, so the minus Emax value. So these are the characteristic points in the butterfly hysteresis. Now, after this small recap, we are going to have a look in the piezoelectric material behavior. As mentioned, we are looking at the small signal behavior. So here's our hysteresis again. We saw in the slides before, but now we assume here in this small range a linear behavior of the piezoceramic. So we only look at not at the full actual usable range, but in a smaller one where we could assume linear behavior to have some simplified equations. And we have, if we look at the strain, we have two effects which contribute to the strain. We have at the one hand the relation between strain and electric field, E. So we have the displacement in the direction lambda, which is equal to d, which is the piezoelectric charge constant, times the electric field. And the electric field could also be expressed of the applied voltage divided by the distance between the electrodes. So strain equals piezoelectric charge constant times the electric field. This is the electric field, or this is the displacement, or the strain in this case, not the displacement, the strain, which is due to the electric field and the inverse piezoelectric effect. And then we have also strains due to mechanical stress, which we also linearize. And there we have the mechanical stress sigma mu, which is applied to the ceramic. And this is coupled with the compliance at a constant electric field to the strain also in the direction lambda. So compliance, the inverse of the stiffness or the Young's modulus in this simplified model. And this exponent E says that the compliance is measured at a constant electric field, because otherwise the compliance would change with the electric field since it alters the mechanical behavior. But we assume one compliance. And then we can superpose these two equations, and we have a composed equation for the overall strain. So strain in the direction lambda is piezoelectric charge constant times the electric field plus the compliance times the applied external stresses. So with this we can calculate the overall strain from the applied electric field and the mechanical stresses. Yeah.
What is causing this mechanical stress?
For example, in the application, the external loading.
But isn't the electric voltage itself causing the inverse piezoelectric effect is like electric voltage causing the stress? So they should be equal, right? Why are they superposed?
Depends on the boundary condition, I would say. If you have the piezoelectric material not, let's say, integrated into a material, and also no clamped or blocked boundary conditions, then it could move freely and does not build up any stress. So we measure the blocking force or the blocking stress if due to the pushback of the force. But it's an external force we would apply to the piezoelectric material. Sorry?
But in free condition, there is no.
Yeah, then in free condition, then this would be 0 here. We will have a look on that in a few slides. Maybe then it's clarified, hopefully. Okay, then we can do the same for the direct piezoelectric effect, where we have the electric displacement D, and this electric displacement can be caused due to a mechanical stress, or here is a force applied. So we have an external force acting on the piezoceramic, and then we have a charge displacement, and this can be described by charge displacement equals piezoelectric charge constant, or piezoelectric charge constant times the external stress. So F divided by the area gives us the stress here, and this then leads to the electric displacement. And the same could be the other way around, so to say. We have, oh, sorry. We could also apply an electric field again, and this electric field times the permittivity gives us also a charge displacement, because the piezoceramic is a dielectric between the electrodes, so it has a capacitive behavior under an applied electrical voltage. And again, we can describe the electrical field also with U divided by L0, so with the distance between the electrodes. And we can again superpose these equations. So we have an equation for the charge displacement from a mechanical stress and the charge displacement from an electrical field. Yeah.
Here we are specifically mentioning a constant mechanical stress.
Yeah.
But here we are not mentioning. Here also at constant electric field. Zero electric field. First, this case. Displacement of mechanical stress.
Yeah, the permittivity is, it has here sigma above, so it is measured at a constant mechanical stress. Yes. Yeah. Okay. So now we have two equations for the electromechanical behavior of the isothermal state, and summarized in the index notation. So we have the charge displacement from the mechanical stress and the electrical field. So the direct piezoelectric effect, and we have the equation from 2 slides before, the displacement, the strain, sorry, from the external mechanical stress and also from the electrical field, which describes the inverse piezoelectric effect, so the actuator effect. So if we use it as a sensor and have a stress or a deformation which causes a stress, then we get a charge displacement. And in this case, if we apply an electric field to use the piezoceramic as an actuator, we would get the displacement. But we could have in both times also the electrical field and the stresses. Come again? The small d, it is where I have it. Here, it's the piezoelectric charge constant. This one? It's also the piezoelectric charge constant, but with other indices for other directions. We will have a look at the directions later on, but it's basically the same physical number. So the relations I presented so far are in engineering notation, but we could also have the nomenclature of solid-state physics or crystallography, and then the strain would be capital S and the mechanical stress a capital T. And as mentioned in the beginning, it's only for the linear small signal behavior, so we don't have the hysteresis in these equations, of course. It's only a very simplified model with some assumptions. And we have the coordinate system here. So x-axis is the 1 direction, y-axis 2 direction, and in thickness, z or 3 direction. We have the rotations about around the 1, 2, and 3 axis, 4, 5, and 6. And most of the time we define that the electrical field goes in the 3 direction. So we will have a look at 2 different, in total 3 different effects, but most of the time the electric field or the polarization direction is defined as in the thickness direction. So here we have the equations for the charge displacement, again in these two notations with the nomenclature of solid-state physics and the nomenclature we are more familiar with in mechanical engineering, and we will use this one. So here we have again the different quantities, electrical displacement density d, or electrical or charge displacement, piezoelectric charge constant, the small d, mechanical stress sigma, 1 epsilon for the dielectric constant at a constant measured at a constant stress, and the electrical field strength E. And regarding the directions, the first index is the of the dielectric constant is the direction of the electric field. So, for example, the 3 direction, and the second index is the direction of the charge displacement. So, the electrical field which causes the charge displacement is the first index, and the effect is the second index. And for the piezoelectric constants, the first index is the direction of the general charge displacement, and the second index is then the direction of the applied mechanical stress. So we have, for example, D31, which would be electric field in 3 direction, and it causes a strain in 1 direction. So it's perpendicular. If we would have D33, we have, it describes the electrical field in 3 direction and also the strain in the same direction as the electric field. So same or similar slide for the inverse piezoelectric effect. We have again the 2 equations in the nomenclature of solid-state physics and in our engineering notation. Here we have the other epsilon for the strain. We have the compliance of the material, S at a constant electric field. We have the mechanical stress, the piezoelectric charge constant again, but with other indices, and we have the electrical field strength. And again, the 2 index, we have the compliance for the compliance constant S. The first index is the strain direction, and the second one is the stress direction. So S11 would be strain in 1 direction and mechanical stress also in 1 direction at a constant electric field. And for the piezoelectric constant D, the first index is the direction of the applied field. So again, 3 direction in this case, and second index is the direction of the generated strain. So the 1 direction in this case. Okay, and then we have different effects we can use for our transducers later on. We have at first the longitudinal effect, where the electric field is parallel to the polarization direction, and this is also parallel to the force or the displacement we want to use. So we utilize the strain in the direction of the electric field. And with this longitudinal effect, we can achieve free strains up to 0.1%. So this is the range we can achieve. This is not that much, and therefore we will have tomorrow a lecture on displacement or stroke amplification. So how can you use this piezoceramics with some additional structures to amplify the achievable displacement to make it useful for technical applications. Then we have the transversal effect. Here the electric field again is parallel to the polarization direction, but we look at the force and the displacement perpendicular to these 2 directions. So it's like the Poisson's effect. So we have the deformation, or the main deformation and the electric field in this direction, but we want to use it perpendicular to it. So we use the strain transverse to the electric field. This is the transversal effect. And here the free strain of the transversal effect is even only 30% of the one from the longitudinal effect. So roughly 1/3 of the longitudinal effect can be used in the transversal effect. And then to be complete, we have also the shear effect, where the electrical field is applied perpendicular to the polarization. So we have here the polarization now in this direction and not anymore from bottom to top, but electrical field stays in the same direction. And then the piezoceramic would be sheared, and we can use the displacement in this direction, so parallel to the polarization, and utilize shear. There are also some actuators who use this effect, but we mainly focus on the longitudinal and on the transversal effect. Yeah, and as mentioned, the most common operating modes are the transverse effect, so D31 and D32 effect, and the longitudinal, the D33 effect. So with the indices now filled out, we have, for example, epsilon in one direction is compliance in one direction times the stress in one direction plus D31 times the electrical field in three direction. And we could also use it in the two directions, so in the other in-plane direction. Then we have to use S22 and sigma 2 and D32, but they are similar. D31 and D32 have the similar behavior, and we still use the field in the thickness or three direction. And then we could, of course, use the longitudinal effect, which gives us the highest deformation or the highest strain, and this would be strain in three direction, and this equals compliance in three direction times stress in three direction plus D33 times E3. So if we speak later on about actuators, then we use the terms D31 and D33 effect most of the time. And here are some examples of actuators shown in different shapes. And then, of course, we could also have the D15 effect. Here's a small mistake. This should be compliance 5,5 and not 4,4. But yeah, it's the similar equation above, but with the other directions. And this would be examples for actuators or transducers which use the shear effect. So now we are coming back again to your question maybe about the blocking force. So we can now use this equation we have for the small signal behavior to look at free displacement and blocking stress or blocking force. We have the strain in three direction, which could also be expressed at the displacement u here divided by the original or the initial length L0 of the actuator. And we look at the D33 effect. So we have this equation again, compliance in three direction times stress in three direction plus D33 times E3. And if we want to look at the free displacement of the actuator, then we don't have an external stress pushing the actuator back. So also no external force, of course. And then we could can use this equation 5, and the external stress is 0. So this is also all 0. And if we then multiply it by the initial length L0 here, then we get this equation for U0, which is the free displacement, which is then L0 initial length times D33 times the maximum field. And we could also, with Emax is the same as Umax times L0 divided by L0, simplify it to D33, which is a characteristic value of the piezoceramic times the maximum voltage we can apply. And with this equation, we can then calculate the free displacement we can achieve. And we can do the same for the blocking stress. Then we set, or we say that epsilon 3 is 0, therefore U is 0. So we have no elongation here. We are at the initial length again because we push it back. So we are in the work diagram at this point. And if we take equation 5 again and say this is 0, then we come up with this equation in the end for the blocking stress. And now we can calculate from characteristic values of the piezoceramic, the D33, the maximum field, as well as the compliance of the material, the achievable blocking stress. So, on to next slide. Now we could also have an external load, or preload or pre-stress. We assume that we have a constant external load, F is constant, which causes a shortening of the actuator. So we have this shortening of the actuator UC, which is the compliance of the material times the stress, so the external force divided by the cross-section times L0. And if we use this in the equation from before, so if we add this to the equation, then we can see now with the hysteresis again to show it, but we are at the small signal behavior, so it would only be a line, but to show the effect, we would shift the characteristic curve just a bit down with a constant loading. So with additional mechanical stress, we can also have this equation with a constant loading and then with varying additional stresses, just to show the behavior of a preloaded actuator, which shifts down this curve in the diagram. So now we are back again at our simplified model. So it's very simplified, I think, with these two stiffnesses of the springs, of the structural material, and of the actuator. But I think it's good to explain the effects. So what an external what the embedded material or the surrounding material does, it reduces the stroke, and this is also what we see in the work diagram. If we have a look at the work diagram again, we have here the free displacement, and we have here the blocking force in this way, and then this has the stiffness Ka, and we have the structure with Ks. They meet at this point. This was the work capacity, and then we can see compared to, so we have a reduced stroke here if we look at the stroke. So this is the new achievable U, and this would be here compared to U0, a high U, and with this surrounding material, we have a lower, maybe right here, EMB for embedded, a lower displacement we can achieve. So how does this look like? We have the actuator embedded elastically in the structure. We have a connection stiffness for the surrounding structure, which is this external force Fs is minus Ks, so the spring stiffness of the surrounding material times the displacement U here. And we can also come again up with our actuator stiffness Ka we already have defined, which is the cross-section of the actuator divided by the compliance times the initial length, L0. And then we can get an equation for the total displacement of the actuator, which is then defined by the electric field, which causes the displacement of the actuator, and also the stiffness is here again, and these Ks divided by Ka is our alpha K again. So this is the ratio of stiffnesses, and we have structural conformity when we have alpha K equals 1, so same actuator and surrounding structural stiffness. And you can also see if we have no surrounding structure, so we assume that Ks is 0, set to 0, then we have here 0, and we divide this by 0, so it stays the same, and then we are back again at the original equation for the actuator only. And if we have here an alpha K of 1, then we divide it by 2, so 50% of the displacement is achievable, and this is also, I have the work diagram, I drew it, so this is also what we see in the work diagram, that we have here 50% of U0 if we have structural conformity, just with this simplified model. So we can enlarge or enhance the model a bit. Here, in this case, we assume that there is surrounding material around the actuator, but not above or below the actuator. And this could be modeled in a simplified model with an additional spring. So we have these springs in parallel and these as a serial spring. And we can also define some additional ratios. So we have our alpha epsilon, which are the stiffnesses again, or in our case now the compliances of the material. So compliance of the actuator, compliance of the structure. So this is the ratio for the stiffnesses between actuator and structure. We can have a ratio for the geometry for the length direction, so L0 of the actuator divided by L0 of the structure. L0 of the actuator is here, and then we have material above with L0 of the structure here. And the third ratio, alpha A, is the ratio of the cross sections. So we have AA for the area of the actuator, and we have AS for the area of the structure. And now we can express the free displacement with these ratios, and can also have a new equation for the blocking force FB, which is then U0 times the overall stiffness of the springs in parallel and in series. So here's GES written for, in German, Gesamt, so overall, or all stiffnesses. And from these two quantities, we can come up with a new definition, or definition for this model of the maximum work capacity we already had yesterday, WA, which is 1/2 free displacement times blocking force. And if we use this blocking force here, then we get 1 divided by 2 U0 squared times the overall stiffnesses of the springs. And with this equations, we can have a look at the work capacities, and maybe we go through the 3 diagrams. I think they are maybe a bit short in the projection, a bit small in the projection, but we have here WA, so the maximum work capacity, and here we say that alpha A is 1, so same cross section of the actuator and the structure, and then we vary here alpha A L for the length and alpha epsilon for the stiffnesses, and we can see that we have here a maximum of work capacity when we have a length ratio of 4. So in this case, we only looked at the interval between 0 and 4. So maximum work capacity at 4, which means that the actuator is in relation to the structure longer, and for the stiffnesses we are not at 1 anymore, but a bit closer to 0, maybe 0.5. And here in this next diagram we set alpha L to 1, so same length ratio or same length between actuator and structure, and then the maximum work capacity is maybe about here, so the stiffness ratio is close to 1, and again we want we now want an area ratio of 4 to get the maximum work capacity, which means more actuator cross-section than structure. And here the last one, here we say the stiffnesses of structure and actuator are the same, and then the maximum work capacity is here. So we want again a high ratio of for the areas, so a lot of actuator area and not so much structure, and also the length ratio should be high, so yeah, again more actuator than structure. But this is only for the simplified model for the springs. It's just to give you an impression about the trade-offs we have to make. So we have to homogenize the stiffnesses and also the geometry to get the maximum work capacity for a smart structure if we use this piezo ceramic materials to deform the structure. Any questions on that? So it will not be an exam question to draw something or to calculate here the stiffness ratio or something else. It's just to give you an impression or a feeling what quantities we have to look at to get the maximum work capacity out of our overall system. We now have a look at the mechanical work and stored energy. So the stored mechanical work in an actuator is caused by the deformation U and the normal force N3. So this is N3 now, normal force in 3 direction. So 1 divided by 2 times N3 times du gives us dWm. So the change or the difference in stored mechanical work. And we can use this equation and replace N3 with the stress times the area. And then we could also replace du using Hooke's law. And then, because this is epsilon, and then we have equation for dWm, sigma 3 squared times the area divided by 2 times the Young's modulus. So this is outside of smart structures or this lecture, this would be E, but we have electrical field E, so the stiffness is epsilon. And then if we multiply it with L0, then we have the mechanical work, or the stored mechanical work. And we could also write it not in terms of stiffness, but in terms of compliance again. So for a blocked actuator, which we excite with the electric field E, we can do the same. We know from the small signal behavior that D33, so the piezoelectric constant in field in 3 direction and effect in displacement in 3 direction divided by the compliance times the electric field gives us a stress, sigma 3. We can replace the field by this equation we already know, and then we can come up with the stored mechanical energy due to the electric field. So on the slide before, we had the stored energy due to an external force, and now we have the stored energy due to the electric field, which can be then expressed like this, D33 squared divided by the compliance times U squared and A divided by L0. Yeah. Sorry? This one. What is missing? The
denominator.
Yeah.
B squared 3 by 2.
Ah, yeah, of course. Yeah. So here it is missing, right? Yeah, thank you. Sorry? Blocked actuator means the actuator is excited by the electric field, but then pushed back again to L0, like if we want to measure the blocking stress or blocking force. This means blocked actuator. Okay. So we can also have a look at the stored electrical energy of the dielectric capacitor, which is 1/2 times the capacitance times U squared, so the applied voltage. And the capacitance can also be expressed at the permittivity in 3 direction at a constant electric field times the area A divided by L0, which is the distance between the electrodes here. And then the stored electrical energy, if we use this equation above and insert this definition of the capacitance, we come up with this equation for the stored electrical energy. So, and since the piezo ceramic converts the electrical energy into mechanical energy, we can come up with the quotient here where we have the mechanical or the stored mechanical energy divided by the electrical energy. Here's the definition of our stored mechanical energy again, and from the slide. From the slide again, from the slide before this, we use the definition of the stored electrical energy. And this gives us this Ki lambda squared, which is the coupling coefficient of the transducer. So it's a measure how good the transduction of the energies between mechanical and electrical energy is of the piezoceramic material. So the K here is the coupling factor, and this is also a key parameter of the piezoceramic materials. Yeah. From the energy ratios, if we use the equations for the mechanical and electrical energy and put them in the equation for the squared coupling factor, then we get this equation. So for the 3,3 effect, so for the longitudinal effect, we have d33 squared divided by the permittivity at a constant stress times the compliance at a constant electric field. And we can also have it more generally for the different directions. And we took the square root to have directly k. Then we have d I lambda divided by the square root of the permittivity in the direction ik and the compliance lambda mu. And the coupling factor is dimensionless, and the measure of the energy conversion, as mentioned, of the transducer, but it's not an efficiency. It does not account for losses. So it's just an expression of how good the transducer is, but without losses. So it's more or less a material parameter. And to give you maybe a better idea of the coupling factor, different coupling factors arise from the orientation scattering of the dipoles, of the polarization in the material. So if we look again at our hysteresis, electrical field, E, and the polarization here. Then we have this point C, and if we polarize our ceramic, then we go up to this point, maximum electric field, and remove it again. Then we have here the remanent polarization. And if we look at our circle diagrams again, so here we have maybe I add another circle of this point here, which is point B. So point B have really a strong or high orientation, and independence of the coupling factor at point C, when we have removed the field, we have still a very high orientation or a lower orientation, and therefore, so this is more efficient in transducing the energies between mechanical and electrical energy. And for perfectly aligned dipoles, so every dipole in the same direction, so this would be only a straight line. The limit is that K33 would be 1. And really high coupling factors can only be achieved with single crystals. So we don't have grains, no polycrystals, just a single crystal. We achieve K33 up to around 0.9, so 90% coupling factor. But the piezoceramic materials we use, the lead zirconate titanate is a polycrystal. It has a lower coupling factor than 0.9. So then let's go to the next slide. And here again, the different effects. So we can also calculate our coupling factors, of course, for the different effects. So we have the transversal effect, the longitudinal effect, and the shear effect, where the directions of the quantities we have to insert change. And therefore, the coupling factor is also dependent on the effect we want to use. So we don't have one coupling factor of the material, but we have one for the transversal effect, one for the longitudinal effect, and one for the shear effect. Then maybe 2 slides on the dynamic behavior. So not much on dynamic behavior, but we could also operate our transducer dynamically, not only apply a static field and remove it again, but have a changing or alternating electric field. And if we look at this, we would have here the electric field in a sine, and then the displacement of the piezoceramic, which follows with some delay also in the sine curve. This is what we saw yesterday on the picoscope, and I think we will also see in the lab. And then we have, for the dynamic behavior, another key parameter, which is the mechanical quality factor. We have here the transmission function, and here are the frequencies. And here's the first resonance frequency, where the amplification of the amplitude is very high, which is depicted by the transmission function. And we can then, if we go to the resonance peak here and have values of minus and plus square root 2 of the left and right from the resonance frequency, we can have these frequencies omega O1 and omega U1. So U1 and O1 and omega O1 and sorry? So the this is omega u, this is omega O, so the letter O, and this is omega 0. Yeah. Sorry? Yeah. So we have the resonance frequency here, which is the, let's say, highest amplification of the amplitude. We are in resonance, and then we look at the values square root of 2 to the left and to the right, and then we have these two frequencies also defined, and we use this because the sharper the peak in the resonance, in the transmission function, the better is the mechanical quality. So if we have not that sharp peak, so maybe this one, then these values were larger, and if the peak is sharper, then they are closer together, and then we would have a higher QM, so a higher mechanical quality factor. Yeah, we won't go into detail into this dynamic behavior, but just to give you an impression, if you look at a data sheet and read something about the mechanical quality factor, then this is meant by this. Then we also have temperature-dependent behavior. We here have from a supplier, PI Ceramics, different ceramic materials, A, B, and C. And we have it here in a diagram from -20 degrees Celsius up to 160 degrees Celsius. And we look at the difference in the dielectric constant. So how does the dielectric constant change normalized with the dielectric constant at room temperature, or at 40 degrees in this case? How does it change over temperature? And we can see that the behavior is temperature dependent, but the variations are not that much. So we have, if we go to low temperatures, we have between -2% and up to 6% difference in the charge piezoelectric constant. And if you go up to high operating temperatures, then we are again at -2 up to maybe 7%. Why can't we go much higher than this? Do you have an idea what the limit, the upper limit of the operating temperature is? Yes, Curie temperature. Why is that the limit? Yeah. Then we have the cubic lattice again, and no piezoelectric effect. Yeah, that's correct. So within the range of normal temperature, these temperature effect can be neglected. If we go to really low, near to cryogenic temperatures, then we only have 20 to 30% of displacement left compared to room temperature. But it still works. So we can use the effect also at very low temperatures, but the displacement gets smaller and smaller we can use. And also the coupling factor is affected. So similar diagram, but now with the coupling factor, the variation of the coupling factor normalized by the coupling factor at 40 degrees. And again, at low temperatures, we have not much displacement left. So Here's the text wrong. It's from the slide before, but you can see there is a difference. So also the coupling factor is affected by temperature. Okay, then coming close to the end of this lecture, we have a look at the characteristic parameters. We have the Curie temperature, which is the temperature of the phase transition from the ferro to the paraelectric state. So the temperature where the lattice changes. We have the compliance, so the proportionally between strain and mechanical stress at a constant field, indicated by the E. We have the mechanical quality factor, which is the measure of the mechanical losses under dynamic behavior, so the sharpness of the resonance peak. We have the frequency constant. We don't have a look in this lecture, so you can neglect it at this place. We have the dielectric constant, which measures the electric displacement in direction I for an electric field in a direction J. So yeah, other indices, but same meaning. Polarization, capital P, is the macroscopic dipole moment. We have the coercive field strength, where the polarization equals out because we have 50% in the one direction oriented and 50% in the other direction. We have the coupling factor, which gives us the ratio of converted energy from mechanical to electrical. And we have the piezoelectric charge constant, which is the proportionally constant into the small signal range between electrical field and mechanical deformation. And with this, we come to advantages and disadvantages of the piezoelectric ceramics. So we have large forces we can achieve. We have a comparably high stiffness. We have a high efficiency of the material and also very short response times. So we can use it for dynamic applications. In static operations, we have very small energy consumption. We can assign different field and strain directions. So we can use the D33 and also the D13 effect. And we have high availability commercially of different ceramic materials. And disadvantages are the temperature-dependent behavior. Even if it's in the, let's say, normal temperature range, it's also neglectable. We can lose the piezoelectric effect due to high temperatures, Curie temperature, due to large field strength, so going above Emax, and also due to mechanical shock. We have a pronounced hysteresis. We neglect in the small signal behavior. And we have significant heating of the ceramic material in the dynamic operation, which also gives us the hysteresis. And we need, as saw yesterday, a high voltage power supply to drive the piezo ceramic. Now, I also have a typical data sheet of this lead zirconate, lead titanate ceramics. So we have 3 strains of 0.1%, so not much. The blocking stress is about 40 megapascals. So this is the stress we could achieve when it's not embedded in a structure. Yeah, frequency up to 20 kilohertz, but we have not gone into detail about this. So the modulus is in 3-3 direction and in 1-1 direction different because we have anisotropic behavior after the polarization. And it's between 40 and 64 gigapascals for this Sonox P53 material. So close to aluminum in the one direction. We have the energy density is different between the 2 effects. Then the coupling factor is 0.74 in this case, so not 0.9 we have at a single crystal, but with this polycrystal we can achieve coupling factors up to 0.74. The Curie temperature is 250 15 degrees. So this is our maximum temperature we can operate the structure then at. Maximum electrical field, 1 kilovolt per millimeter, so lower than we saw in the plots before, but this is a different material, and the density around 7, so similar to steel, maybe the density or close to steel. But you can see that with these stiffnesses or Young's modulus, it's still usable also as a structural material, and therefore this is really a multifunction material because we have the piezoelectric effect, and it's also capable of bearing some loads. So last slide, summary. With the D33 effect, we have free strains of about 0.1%. The free strain in the D31 effect, so the transverse effect, is approximately 30% of the D33 effect, so much lower. We assume that the volume remains constant during actuation. After polarization, the behavior is, so the electrical and also the mechanical behavior is anisotropic, which we saw in the Young's modulus, which is in D31 direction 30% greater than in D33 direction. We introduced some characteristic parameters for the small signal behavior, neglecting the hysteresis. And in large signal operation, we have a hysteresis or loss of 8 to 15%. And towards lower temperatures, the active strain decreases by, if you want to have it linear, as a linear number, about 0.2% per Kelvin. And with this, I'm at the end of this first lecture today, and I'm open to questions.
Dynamic behavior, like
yeah.
Alternating current.
Yeah.
So does that create a lot of
heat
operational problems?
I think the piezoelectric material is quite good for dynamic behavior because you also use it for structural health monitoring, where you excite the structure with a burst signal, so with a sine wave with different amplitudes, and also collect it with the sensor again. But I have not much hands-on experience with dynamic behavior, to be honest. But I think it's a good material for dynamic applications also. Yeah. By single crystal, I mean that the crystal has no individual grains, but this would be a polycrystal, and a single crystal is only one large crystal lattice, so you have no grains in it. Yeah. Okay. Further questions?
So how do you define 1,5
D15? How we define it? You mean how we measure it, or how do we?
Directions is asking.
Okay. So we go back to here. So we have the where I have the definitions of the D. So it's direction of the applied electric field is the first index. So in one direction, we have the electric field, and in 5 direction, 4 or 5, we have the generated strains. So it would be shear in this or that plane then. But you won't need it for the exam. So we really focus from now on D33 and D31 effect for the transducers. Okay, then we have a look at the timetable.